Hello, I'm Dr. Dupre, and in this section we're going to discuss moments and centers of mass. Let's look at how we define the moment in this case for a thin rod about the origin. Moments, mass, and center of mass of a thin rod or strip along the x-axis with density function delta of x. The moment about the origin, which is denoted capital M with a subscript 0, is the definite integral from a to b of x multiplied by delta x dx. The mass, capital M, is the definite integral from a to b of the density function delta x dx. And the center of mass, denoted x bar, is the moment m sub 0 divided by the total mass m. Notice if I take that equation for the center of mass, multiply both sides by capital M, it gives me the formula m sub 0 equals x bar times m. Notice up here in the integral for m sub 0, the integrand is x delta x dx, whereas for the mass, the integrand is delta x dx without dx. This delta x dx you can think of as a little bit of mass that's lying right at x. How much is it? Well, delta x is the density there, so a little bit of the mass with a variation in x by amount dx would produce delta x dx as a mass, little bit of mass. We might call this dm. It's a useful concept, dm, for a little bit of mass. And notice what we have up here. The m0 is the integral from a to b of x dm, which I could write. If I replace that by dm, this becomes the integral from a to b of x dm. So, in effect, x dm is the moment of this little bit of mass in amount dm, which is situated x units from the origin. And so when I look at this formula right here, it's in effect telling me that the moment about the origin is x bar, the coordinate of the center of mass, multiplied by the entire mass. It's as if, as far as moment-wise, it's behaving as if the entire mass, capital M, were situated at the single point x bar. If it were, its moment would be m0 equal x bar times m. And so, in effect, this is a kind of an averaging process. We found the average of the x coordinates of all the material in the thin rod. Well, when I think of the center of mass of a thin rod, I really should be thinking of the point where the rod balances. In other words, if I'm holding a thin rod, like for instance this pen, and I look to see where it balances, that would be the center of mass. So let's work out, before we start any problems, let's work out the simplest case. What's the center of mass of a thin rod of constant density? So here I have a thin rod of constant density equal delta laying out along the x-axis over the interval from a to b. So the mass is the definite integral from a to b of delta dx, so naturally that's just the constant delta multiplied by b minus a. The moment is the definite integral from a to b of x times delta. Well, delta is a constant, and so we're just integrating x dx from a to b, and so that's x squared over 2 evaluated between limits a and b is simply delta over 2 b squared minus a squared. That's the moment. Well, notice b squared minus a squared factors as b minus a times b plus a, or a plus b, and let's put the 2 under the a plus b. So we can think of the moment as delta times b minus a, all multiplied by a plus b over 2. Well, notice the delta times b minus a, this part, is the mass already. So if I divide this quantity by the mass, all that's left is a plus b over 2. Well, notice if you have a rod along the x-axis and the left end point is at a and the right end point is at b, it's a thin rod. So there it is, lying along the x-axis. What's the significance of a plus b over 2? That's the dead center point. right between A and B. And if the density is constant, then obviously the rod is going to balance right there on its center. Now let's work an example where we find the mass and moment of a thin rod with varying density. So in this case, our density function delta of x is given as 1 plus the quantity x over 3 for 0 less than or equal to x less than or equal to 3. That's the density of our thin rod, and we want to find the mass, the moment about the origin, and the center of mass. So using our formulas then, the mass will be the integral from 0 to 3 of the quantity 1 plus x over 3 dx. The moment is in effect the same integral with an extra factor of x put in, definite integral from 0 to 3 of x times the density 1 plus x over 3 dx. And of course the center of mass is simply the moment divided by the mass. That is, we take the answer to this integral and divide it by the answer to this integral. Okay, so let's begin by working out the mass. Notice the mass then is just the definite integral, an easy one to do. And so the antiderivative of 1 is x. The antiderivative of x is x squared over 2. So we have 1/3 times x squared over 2. And that's to be evaluated between limits 0 and 3. So obviously putting in 0 gives nothing. We just have to put in the 3. So we have 3 plus 3 squared divided by 3 times 2, which is 3 plus, well, we can cancel 3's here, and that just leaves a 3/2 for our second term. 3/2 is 1/2. 3 and 1/2 is 4/2, which we could write as 9/2. That's the mass of our thin rod. Now next what we want to do is work out the moment of our thin rod. And so that's the same integral. Notice what I've done here. It's the exact same integrand with an extra factor of x. So let's work that one out next. So in this case, multiplying the x through, we have as our integrand x plus 1/3 x squared, and that's to be integrated from 0 to 3 dx. And so the antiderivative of x is x squared over 2 plus 1/3 antiderivative of x squared, which is x cubed over 3, and that's to be evaluated between the limits 0 and 3. So now let's put our upper limit in. The lower limit gives nothing, so we get 3 squared over 2 plus 3 cubed divided by 3 times 3, which is again 3 squared. And so consequently we have 3 cubed over 3 squared is a 3, and this is a 9/2. 9/2 plus 3. Well, what is 9/2? 9/2 is 4.5, so in effect we're getting 7.5 or 15/2. So remember our moment now then is 15/2. And what was our mass? Remember the mass was 9/2. So to find our center of mass, we're going to divide the 15/2 by the 9/2. So let's, just remind ourselves, center of mass is moment divided by mass. And so the moment m0 is 15/2. The mass m is 9/2 from our previous computations. And so now the center of mass, which is denoted by x bar, is m0 divided by m, 15/2 over 9/2, which is 15/9. And of course we can cancel the 3's out of this expression and get simply 5/3. Now let's work a problem where we're working out the center of mass of a thin rod, but the density function is not given by a single equation. So here we have the density of a thin rod given to us, delta x equal 2 minus x when x is from 0 to 1. That is 0 less than or equal to x less than or equal to 1. And it's simply x for 1 less than or equal to x less than or equal to 2. Notice when x equals 1, either expression gives the value 1. So we don't have to worry about saying 0 less than or equal to x less than 1, for instance, and x greater than or equal to 1 here. In any case, that's our density function. And notice in integrating this, we're going to have to integrate from 0 to 1 using this expression, and then from 1 to 2 using this. We want to find the mass, the moment, and the center of mass. Okay, so for instance, since our density function is given by these two expressions, our mass is the integral from 0 to 2 of delta x dx, which is the integral from 0 to 1 of delta x, which is over this range from 0 to 1, simply 2 minus x. So consequently, our first term is integral 0 to 1, 2 minus x dx, plus the integral from 1 to 2 of delta x, which would be simply the integral of 1 from 1 to 2 of x dx. Now, these are easy integrals to compute. The mass, capital M, we just simply anti-differentiate the 2 minus x, which is 2x minus x squared over 2, and that is to be evaluated from limits 0 to 1, plus antiderivative of x, which is x squared over 2, and that's to be evaluated between limits 1 and 2. Well, notice in this first evaluation, the lower limit gives 0, so I just have to put in 1. When I put in 1 in the upper limit, I get 2 minus a half. And then plus what I get by evaluating x squared over 2 from 1 to 2, that is, first put in the 2, that's 2 squared over 2, minus what I get by putting in the 1, which is simply a half. And so consequently, notice what I get. 2 squared over 2 is 4 over 2 is 2. So I have 2 minus a half here, 2 minus a half here. That's 3 halves plus 3 halves, which is, of course, simply 3. And so our mass here, M, is simply 3. Well, we've worked out the mass for our problem. Next, we're going to work out the moment. So our density function delta x, remember, is given by 2 minus x in the interval 0 to 1, whereas it's simply x in the interval from 1 to 2. Our moment is the integral from 0 to 2 of x times delta x dx. So again, this will have to be broken up as the integral from 0 to 1. In that range, delta x is 2 minus x, so our integrand is x times the quantity 2 minus x, plus the integral from 1 to 2, x times delta x, but in this range from 1 to 2, delta x is simply x, so we have x times x, or what amounts to x squared. So that's the integral we have to calculate for the moment, m0. And so now the first step would be, in this term, let's multiply out the x through the 2 minus x. So consequently, get integral 0 to 1, 2x minus x squared dx, plus the integral from 1 to 2 of x squared dx. Well, the antiderivative of x squared is x cubed over 3, and that's to be evaluated from 1 to 2. So now coming back to our first term, the antiderivative of 2x is x squared. The antiderivative of x squared is x cubed over 3. So our antiderivative is x squared minus x cubed over 3. And that's to be evaluated between limits 0 and 1. And of course, over here in this second term, x cubed over 3 evaluated between limits 1 to 2. Putting in the upper limit 2, we get 2 cubed, or 8 thirds, minus 1 third. So now here we put our upper limit 1 in. 0 will contribute nothing, so we have 1 minus a third plus 8 thirds minus a third. Well, let's see. 1 minus a third is 2 thirds. 8 thirds minus a third is 7 thirds. 2 thirds and 7 thirds is 9 thirds, which is 3. So our moment, m sub 0, equals 3. So notice what we've arrived at. The mass m is 3, and the moment m sub 0 is also 3. Well, now let's calculate the center of mass. Remember, the center of mass is simply m sub 0 divided by m, and both of them were 3. So for our center of mass, we have 3 over 3, which is simply 1. Well, now let's look at the concept of moments and center of mass for a thin plate in the xy plane. Moments, mass, and center of mass of a thin plate covering a region in the xy plane. Here I've drawn a little picture of a region enclosed by a curve, and let's imagine that we've divided this region up into thin strips, and here's the thin strip over x. Now, to begin with, let's assume that the density of this thin plate is a function of x alone. So consequently, all along this thin strip, the density is constant. Well, we worked out the center of mass of a thin rod with constant density. Remember, it's right at the center of the rod, and so consequently, if that vertical strip has constant density, then its center of mass is right here at this center point. In other words, the x tilde, which would be the center of mass, the x-coordinate of the center of mass, or the balance point of that thin rod, is certainly x, and the y-coordinate of the balance point of this thin strip, its center of mass, denoted y tilde, is simply the middle point of that little thin strip. So in any case, that gives us the center of mass of that little thin strip. Now that little thin strip has a certain mass, which we could call dm. And so that little thin strip, think of it as having mass dm, and its center balance point has coordinates x tilde, y tilde. And so by definition, its moment about the x-axis is the integral of y tilde dm. That is, about this axis here, we're trying to average the distances of points in the thin plate according to their density. So there we get m sub x equals definite integral y tilde dm. Of course, this integral doesn't have limits on it. The limits would be provided by the specifics of a given problem. The moment about the y-axis, m sub y, is the integral x tilde dm. Of course, the mass m itself is just the integral dm, and then by definition, x bar is my over m, y bar is mx over m. Notice that here for mx we have y tilde, and consequently x bar, or rather y bar, is mx over m. In other words, what I'm dividing here, mx over m, is the integral of y tilde dm by m, and so that's in effect the average of the y coordinates, y tilde. The my is the same for the x's. In other words, you're averaging here. When I divide my by m, I'm in effect getting the average of the x tildes. And so in effect, then, the center of mass has coordinates x bar, y bar. Well, let's look at an example where we work out the mass, the moments, and the center of mass for a thin plate of constant density. So here we want to consider a thin plate, density equal delta equal constant, and our plate is the region in the xy plane bounded by the curves y equal x minus x squared and y equals negative x. So what we have to do is begin by looking at a picture of those curves to see what our region is. Well, the curve y equal x minus x squared, of course, is this downward parabola which crosses the x-axis at the points 0 and 1. And our other line, y equal negative x, forming our other boundary, is just this straight line, slope equals negative 1, going through the origin. And so here's our region, this little region between the parabola and the line. And so what we want to do is look at a typical vertical strip, and so it's the mass of that strip that we want to consider as well as its center of mass. Notice the center of mass is the center point of the little thin strip. Now, our strips are vertical, so the center of mass x tilde is just x. What about the y tilde? That's the center. That's the average of that height and that height. In other words, it's the average of the y coordinate on the parabola x minus x squared and the y coordinate on the line, which is negative x. So we have x minus x squared plus negative x over 2 is y tilde. Well, notice in this case the negative x cancels the x, and so we're ending up here with simply negative x squared over 2. So just to summarize then, x tilde is x and y tilde is negative x squared over 2. So what's our dm? Our dm, in effect, is the length of this little strip multiplied by delta, which is the density, times the dx. And so consequently, what we're getting for the mass is simply the area between the two curves multiplied by delta. And of course, we know how to find the area between two curves. You just integrate the difference of the top one minus the bottom one. Well, we see what dm is for this problem and what x tilde and y tilde are. But next we have to figure out what are our limits of integration going to be. Let's look at a picture. Okay, so to find our limits of integration, what we need to do is look at the picture of our two curves. Notice where they intersect gives the x coordinate of how far we integrate. So they intersect here at x equals 0, but where do they intersect over here? What's the x coordinate of that point? Well, to find it, we have to solve x minus x squared equals negative x. So let's do that. We have to solve the equation x minus x squared equal negative x to find our right-hand limit of integration. So put the term over to the left side of the equation. The negative x becomes a positive x over here, so positive x and x is 2x minus x squared equals 0. So factor out an x. We have x times the quantity 2 minus x equals 0, and we see the two solutions are x equals 0 and x equal 2. We already realized that the curves cross at x equals 0 is the x equals 2 that we're really interested in. And so that means our limits of integration are from 0 to 2. Well, now let's look at our expression for dm and calculate the mass. Okay, so remember y equal x minus x squared, the parabola pointing down or opening downward is on top. Y equal negative x, the line is on the bottom. And so our dm is the y value here minus the y value here. That is, dm is delta, the density, which is constant, times the quantity x minus x squared minus the negative x, and all multiplied by dx. Well, negative x is a positive x added to x gives 2x. So the dm is delta times the quantity 2x minus x squared dx. And so that has to be integrated from 0 to 2. So our mass is finally the integral from 0 to 2, delta times the quantity 2x minus x squared dx. So the delta is just constant, so it comes out of the integral. Antiderivative of 2x is x squared minus the antiderivative of x squared, which is x cubed over 3. That's to be evaluated between limits 0 and 2. So we get delta multiplied by 2 squared is 4 minus 2 cubed being 8. We have minus 8 thirds. Well, 4 is 12 thirds, and 12 thirds minus 8 thirds is 4 thirds. So we get 4 thirds delta for the mass. All right, we calculated the mass. Now let's calculate the moment about the x-axis, capital M sub x. Remember, capital M sub x is the definite integral from 0 to 2 of y tilde dm. And the dm is delta times the quantity 2x minus x squared dx. And remember, the y tilde is the negative 1/2 x squared. And so consequently, this is our integration problem. We would begin by bringing out the factor negative a half. And so we have negative delta over 2 times the integral from 0 to 2, and we'll take the x squared and multiply it through. So x squared times 2x is 2x cubed minus x squared times x squared is x to the 4th dx. So negative delta over 2, antiderivative of 2x cubed is 2 over 4 x to the 4th minus antiderivative of x to the 4th is x to the 5th over 5, and that's to be evaluated between limits 0 and 2. Well, if I put the 2 in for the upper limit here, the upper limit 2 in for x everywhere, I get negative delta over 2. 2 to the 4th is 16, and 2 over 4 is a factor of a half, so a half of 16 is 8, minus 2 to the 5th is 32, divided by 5. Now 8 is 40/5, so 40/5 minus 32/5 is 8/5. So we have negative delta over 2 times 8/5, or 8 over 2 being 4, that's negative 4 delta divided by 5. And so there is our moment about the x-axis. Okay, now let's find the moment about the y-axis. The moment about the y-axis, remember, that's denoted capital M sub y, is the integral from 0 to 2 of x tilde dm. And remember, x tilde is just x, whereas the dm is delta times the quantity 2x minus x squared dx. So we begin by multiplying the x through. We have integral from 0 to 2, 2x squared minus x cubed dx. So the antiderivative of 2x squared is 2x cubed over 3 minus antiderivative of x cubed is x to the 4th over 4. This is all multiplied by the constant density delta, and that's to be evaluated between limits 0 and 2. Well, of course, putting in 0 gives us nothing, so we just plug in the 2. 2 cubed is 8 times 2 is 16, so the first term is 16/3, minus 2 to the 4th is 16, so that's minus 16/4. So we get, factoring out the 16, 16 delta times a third minus a fourth. Well, a third minus a fourth is a 12th, so we get 16/12 delta. And of course, here we can cancel 4s, and we'll get 4/3 delta as the moment about the y-axis. Okay, now we've found our mass and our moments, so let's use that information to find the center of mass. So in summary, we found the mass is 4 delta over 3. The moment about the x-axis, m sub x, is negative 4 delta over 5, and the moment about the y-axis is 4 delta over 3. Now remember, x bar is m sub y over m, and so let's put that in. M sub y, 4 delta divided by 3, divided by the mass, which is 4 delta divided by 3. Everything cancels. X bar is 1. Y bar is m sub x, that's negative 4 delta over 5, divided by 4 delta over 3. Notice the 4 deltas cancel, and so we've just got negative a fifth divided by the third, which is simply negative 3/5. So x bar is 1, and y bar is negative 3/5. and there, in effect, is our center of mass. Now let's look at the situation for finding center of mass for a bent wire or a curved rod. Suppose we have a thin curved rod or wire that's bent into a certain shape. Here, imagine this curve is actually a wire, and it's got density delta at each point, and so ds is a little bit of arc length along this curve, and so the little bit of mass dm is simply the density times the little bit of length ds. Of course, we know how to calculate ds if the curve has been parameterized by the parameter t. ds is the square root of dx dt squared plus dy dt squared, all times dt. For instance, if our curve is the graph of a function y equal f of x, I can take x as the parameter t, and so dx over dx is simply 1, and we get 1 plus dy dx quantity squared. Or if we were to parameterize by y, we would have 1 for this term plus dx dy quantity squared times dy. In any case, this little bit of wire here, obviously we'll think of it as just being centered at the point xy if x is the location of the point where the little bit is. X comma y is the center point of the little bit ds, and so consequently the x tilde in this case is just x and the y tilde is just y. Okay, now let's work out an example where we compute the center of mass for a bent wire. For wires and thin rods of constant density shaped like circular arcs centered at the origin and symmetric about the y-axis, the y-coordinate of the center of mass is y bar equals a sine alpha divided by alpha, which is also equal to ac divided by s. And here for these symbols, a is the radius of the circular arc, and twice alpha is the angle of the endpoints subtended at the center of the circular arcs. That is, those circular arcs are parts of circles, and those circles have a center, in this case at the origin. Well, let's look at a picture here. Here's a picture. Here's our circular arc of wire or thin rod, and it's symmetric about the vertical axis, the y-axis. And so here I've got the origin, and the straight line from the origin out to the right end of the wire subtends an angle alpha with the vertical axis. Likewise, the straight line from the origin to the left end subtends angle alpha with the vertical axis. And so consequently, here our center of mass is somewhere along the y-axis. How do we know that? Well, symmetry immediately tells us that as far as the x-coordinate of the center of mass is concerned, it certainly has no right to be on either side. It certainly has to be right in the middle. Whenever you have symmetry working for you, the center of mass will be on the axis of symmetry, and so we see that the y-axis is itself is an axis of symmetry, and so therefore the center of mass is on it somewhere. In effect, that tells us right off x bar equals 0, and we only have to find y bar. Now, in order to do this, we could parameterize this circular wire in many ways, but the simplest way to go here is to just remember that we can take our angle theta as a variable. And so if I take a straight line from the origin coming out here to some arbitrary point on the wire, and let's make this angle be theta. So here we are at angle theta. A little bit of variation in theta, notice, causes a little bit of variation along this wire. So there's our ds here. And so how is it related to d theta? A little bit of variation in theta. Well, we have a radius a, and so we see right off that ds is simply a d theta. Now, what we're trying to find is the y coordinate of the center of mass, so we want to be averaging the y tildes against dm, And so what is the y tilde for this particular point? Remember, it's just the y coordinate of that point, and the y coordinate of that point is a sine theta. So here we have ds is simply a d theta, and y tilde is y, which is a sine theta. So we have exactly what we need to integrate. So in terms of the angle theta, we know dm now, and we know what the y tilde is. Now let's look to see how we find our limits of integration. So here's our picture again. Notice our angle here is alpha this way and this way. And theta, of course, is measured from the positive x-axis. So our theta is going to vary from pi over 2 minus alpha all the way around to pi over 2 plus alpha. That is, we're going to be integrating from pi over 2 minus alpha to pi over 2 plus alpha. Remember, our y tilde is a sine theta. ds is simply a d theta. dm is delta ds, so therefore dm is delta a d theta. So how about our mass right off? Well, obviously the mass, since the density is constant, is just the length of the wire times delta. The length of the wire, of course, is simply a times the total angular separation of the two endpoints here subtended by the origin, so that angle is 2 alpha. So the mass here is delta A 2 alpha. There's our mass. Now we're ready to find the moment about the x-axis, m sub x, which will be the integral of y tilde dm. So m sub x is the integral from pi over 2 minus alpha to pi over 2 plus alpha of y tilde dm. Remember, the y tilde is a sine theta, and the dm is delta a d theta. So that's the integral we have to finally compute. Now we can take the constants a out. There were two factors, so m sub x is delta a squared times the integral from pi over 2 minus alpha to pi over 2 plus alpha of sine theta. Well, the antiderivative of sine theta is negative cosine theta. So we get negative cosine theta evaluated between the limits pi over 2 minus alpha and pi over 2 plus alpha. So that's delta a squared times, and now having a negative sign there means we can have effectively put the pi over 2 minus alpha into cosine theta first. Cosine pi over 2 minus alpha minus cosine pi over 2 plus alpha. Now, you might recall that among the trigonometric relations, in fact, this is the very definition sometimes of the cosine function. That is, the cosine of an angle is the sine of the coangle, and likewise the sine of the coangle is the cosine of the angle, and so forth. So cosine pi over 2 minus alpha is simply the sine of alpha. So here we have sine alpha. And likewise, when we use our sum formula for the cosine in terms of sine and cosine, the cosine of pi over 2 plus alpha will be the negative of sine alpha. So we have sine alpha minus negative sine alpha, which is in effect 2 sine alpha. Okay, we've calculated our moment about the x-axis, and we know the mass. Let's put it together. So our moment about the x-axis is delta a squared times 2 times sine alpha, whereas our mass is delta times a times 2 alpha. So y bar is m sub x divided by m, so that's delta a squared times 2 sine alpha divided by delta a times 2 alpha, and of course now just about everything cancels except for one factor of a, the sine alpha in the numerator and the alpha down in the denominator, and so y bar is a sine alpha divided by alpha. Okay, we have our first formula for the center of mass of the circular arc of constant density. Now let's look at the second formula. Remember, our formula is y bar equals a sine alpha divided by alpha, which also equals ac divided by s. Here s is the arc length of the circular arc. C is the distance between the endpoints. So let's look at the picture again. Here's the picture. Notice the C here is this horizontal distance between the two endpoints A and B of this bent rod bent into a circular arc. The radius here is A, and so one thing we can notice is this distance right here is the side opposite this triangle. It's a right triangle. Here's the 90-degree angle right here, and here's the angle alpha. This side is opposite angle alpha. Consequently, this distance from this point to B is A sine alpha. So A sine alpha is this distance from here, the y-axis over to B, which is the same as the distance from the origin to this point, and by symmetry that is half of the distance C. So we can say A sine alpha is simply C divided by 2. On the other hand, recall the arc length S here is simply 2 alpha, that's the angular spread, multiplied by the radius. So we have 2a alpha. And looking back at the formula we want to see now, remember we want to see that y bar is AC over S. Okay, so let's look at those ingredients then. We have A sine alpha equals C divided by 2. S is equal to 2a alpha. And so consequently, y bar we've already seen is a sine alpha divided by alpha. So the numerator is c over 2 divided by alpha. So bring the 2 down to the denominator. We have c divided by 2 alpha. So multiplying top and bottom by a, in the numerator we get the ac, which we want. And down here we have the 2a alpha, which is s. And so we finally get ac divided by the arc length s, which is our other formula for y bar. Okay, we've worked some problems on centers of mass for thin rods, for thin plates, and for bent wires. Now that you've seen these problems work, you should try some on your own.